The transformer that you see is a 250 watts transformer. The two terminals, yellow and blue, these two are secondary low voltage high current winding output terminals on which 24 volts 10 amperes appear. And these two red and yellow wires, these are the 220 volts input side of this transformer. The bolts that this transformer initially had got lost, so I used the pretty longer ones, although I could cut them with an angle grinder from here, but still it is not creating any problem, so I'm going to stick with these. Okay, so let's do the continuity check on this transformer with the help of a multimeter. So the multimeter is pointed towards the continuity checking mode. Okay, so first the low voltage secondary winding high current side. Yeah, it's working. Now comes the high voltage side. Yeah, the high voltage side, you can see the resistance is somewhere around 9 ohms, and here you can see that the resistance is only 2 ohms. Okay, so this makes sure that this is the high current side and this is the high voltage low current side. So guys, with that being done, let's connect 220 volts AC supply to check its output. Okay, connecting it to the supply. At present the supply is turned off just for safety purposes. Now I will turn it on and connect a multimeter on these two terminals, and it should give me some voltage at the meter screen. So let's also connect the meter. The output is obviously going to be AC, so pointing towards 200 volts AC mode. So guys, now I'm going to turn on the supply and you should see some voltage reflected on the display screen. Keep watching. So guys, here as you can see that the output voltage is somewhere around 27.2 volts. They have increased the voltage from 24 to 27 because when they connect an actual good amount of 10 amperes load, then the voltage will automatically get dropped to 24 volts. So this way they can maintain the voltage and current by increasing the voltage, open circuit voltage. Okay. So guys, this bulb that you see here is 250 watts. You can see here 24 volts, and the side of it is written 250 watts. So I'm going to use this bulb to check its output current. So 250 watts means that it is going to draw 10 amps from this transformer. Okay, one terminal like this, another one like this. Yeah, it is getting really hot. Once again, oh yeah, it's very hot. So the transformer and supply and the bulb, all of them are working perfectly fine. Now it's time to go to the next step. So guys, for this kind of setup, we are first going to need a bridge rectifier. I'm going to use a 35 amps rectifier, which is the most common available in the electronics market. It's a single phase rectifier, Vanco. So AC terminal is this one, the black one, thick one. So diagonal opposite is also the other AC terminal. Remaining two are the DC terminal, since this black one is positive and then blue one is going to be negative. So let's connect it to the AC supply from the output of the transformer. Okay, so this has been connected. Now the DC terminals, let's interchange the black and blue terminal because usually the black is used for negative. So now blue is the positive and black is the negative. So guys, since we are not using this terminal, so let's cover it with tape. It might contain some AC ripples. Okay. So guys, now comes the part where I'm going to add the filter circuit to this transformer. Although I'm not going to actually add the filter circuit, all I'm going to do is purify the DC coming out from the rectifier with the help of this simple capacitor. You can see it's rating 31,000 microfarad at 50 volts DC, and this is producing somewhere around 27.7 volts. So this capacitor suits pretty good for the job. Okay, so this has polarity, as you can see, plus, and this one is minus, so it has to be connected to the circuit accordingly. Hey guys, don't forget to subscribe my channel and hit that bell icon for similar video notifications. Also, do comment on what else you would like me to add to this present video. Best regards, Electron. So guys, here as you can see, I've added the capacitor and the setup is fully complete. Now when I will measure the voltage with this multimeter, it is going to be a little more than the measured voltage without the capacitor and rectifier. Even though there is forward biasing voltage drop across the rectifier, still the overall output voltage is going to be more. I think it is going to be more than 30 in DC. So let's point it towards 200 volts DC mode. Okay, and touch the meter. You can see the voltage increased from 27.7 volts to 38.8 volts. Because initially when the meter was connected in AC, it was measuring the average value. But now when it is connected to the capacitor, it is measuring the peak value, the highest voltage point to which the capacitor can get charged. So the capacitor gets charged to that value and this meter reflects the charge on the capacitor. So guys, one final check. So the voltage is close to 39 volts. So guys, this what you see is an electric screwdriver that I made from a 220 volts old drill machine that was not working initially. So it runs on 30 volts power supply. So I'm going to run it with this power supply just for testing. The video for modification of this drill machine to DC drill is still in my video list. You can check it out. So you can see the wire, connecting it like this and pressing this button. You can see it is working perfectly. Now comes the other way. Okay, working really nice. So the DC supply is working pretty good. And guys, in one of my previous videos you saw me modify this high-speed air blower, and I used this DC motor. As you can see, it's a 12 volts high current DC motor. You can see the winding is so thick. The current intake is somewhere around 32 amperes. So many of you said, oh, the voltage is not enough, or the speed is very low. So I'm going to test this blower with this power supply. Yeah, this one is strong. So both the terminals have been connected. Now it's time to test it. Okay, so guys, the supply has been connected. Let's turn it on. Yeah, I think now it's high speed enough for you people, right? Although because of the Murphy's law, it always operates in the opposite direction if we connect the wires without considering the polarity. So let's connect it in the opposite. Okay, so initially you didn't hear the sound of a wind, but now you will. Yeah. Okay. So assuming that this is some garbage, which it actually is, at least now it is, so let's push it away. Yeah, so you can see it is working at a really good speed. So guys, now let's connect this 12 volts 32 amperes DC motor, a similar one of which I used in the air blower that you just saw. Okay, so it is going to make a lot of spark. The current is going to be very high. Oh, actually I turned off the supply and it sparked just for a second because the capacitor was charged. So beware with that, guys. The capacitor is charged and the voltage is very high. It's very dangerous. Okay, once again. Holy crap. All the dust, I haven't used it for many months, so because of which there was dust all over inside the armature. Once again. Oh, the wire got stuck. Yeah, it's working at a pretty good speed. The power supply is very good. And one more thing, guys, this capacitor that I have added to the end of the rectifier, it adds up to the short circuit current. So the meaning of this is that if this transformer is capable of producing or converting around 10 amperes, then this capacitor will add up to that 10 amperes and increasing its amps just for a millisecond or 1 second, like doubling up the amps to 20 amps or 30 amps. So guys, this is the long halogen 220 volts and 1000 watts. Okay, you can see that is very long, just like a stick, and the filament is also very thick. And because the filament is thick, I can glow this halogen even at just 40 volts. Although the illumination is not going to be so great, but still it is going to work. Okay, so let's connect it. So guys, you can see that it is glowing. So guys, you can see without the lights, it is glowing pretty good. Looks really nice. Okay, so guys, this is a 180 volts, 7.5 amps, 1.5 HP, 4000 rpm PMDC motor, large PMDC motor that I'm going to use to test this circuit. Okay, so these are the two terminals, red and black. So let's connect them to the capacitor output terminals. Okay, so the first one is connected. Now comes the second one. And obviously the motor is big, and because of the inertia disk, it is going to create a short circuit for some time because the moment of inertia is 0 at present. Okay, you can see that it is running pretty good. A 1.5 HP DC motor that is running flawlessly, and it is almost unstoppable. Yeah, it is unstoppable with hands, of course. It is very strong at 40 volts, and its full power will be seen at 180 volts. At present it is only 40 volts. Hi guys, welcome back to my channel Mr. Electron, and today in this video I'm going to teach you how to make inverter. So let's start with the power transistor that I'm going to use in this project. Here you can see ST13009 power transistor. I'm going to use 4 pieces of these. Okay, if you don't get these or don't have these, you can also go for this MJE13009 power transistor. Works just the same. And I'm also going to use this circuit, inverter circuit, that I showed you in my previous video. If you haven't seen it yet, link will be provided in the description, so don't forget to check it out. These two are the big heat sinks that I'm going to use for this project. You can see that initially it was a single piece, but then I used an angle grinder and I split it into 2 as evenly as I could. It's from an old UPS. You can see a lot of oxidation on the surface of the heat sink. I will have to remove it here now. So let's start with that. Well guys, the surface cleaning process has completed. It's time to place the power transistors. The transistors, as you can see guys, are now well placed. Now guys, I'm going to install the full inverter setup on this wooden board. It's supply actually. And these are the heat sinks for the power transistor. One piece, yeah. Let's drill around 2 holes on here, the other one on here. Next for this piece, one here, the other one here. Okay. So here, as you can see guys, that I have placed these nuts and bolts to keep the heat sinks in place. You see, just perfect. Now comes the connection part. Here guys, the two transistors on this heatsink are going to act as one big transistor, and same for this one. This is one transistor, both will be connected in parallel, and these two also will be connected parallel. So the lowest terminal over here, you see this one, this is the base, you see, and this one is also base. So what I'm going to do is I'm going to move it like this. Okay, same for this one. Yeah, so here as you can see that I've bent the base terminal like this to connect them in parallel and separate it from the collector and emitter. Now base for these two, this one upper one is base for this one, and yeah, base, yeah, base, collector and emitter. So guys, here I'm going to use this green wire as base, which is this one and this one. I'm going to short these two. I'm going to solder them together. Guys, as you can see that I'm using green wire for the base, red for the collector, and I'm going to use black wires for the emitter terminals. Now guys, here I'm going to connect the black wire as the emitter. Okay, one terminal connected, second terminal also connected, remaining is the third and the fourth terminal for the emitter. Yeah, the last terminal has also been connected. As you can see, the last emitter terminal, of course the remaining three emitter terminals, all have been connected perfectly. Now guys, you've already seen this circuit. What I have done to this is I have removed the black emitter wire that was connected to these two. This one, it was connected like this, okay, and I have removed it because it is not needed in this circuit. So it's time to connect this circuit to the main circuit. So guys, the plastic has been stuck pretty good. Okay, now comes the time for connecting these two terminals to the heatsink transistors. Now guys, these two green wires are coming out from the collector terminals of these two transistors. Okay, the middle collector terminal. So these two wires will be connected to the collectors of the transistors of these two heatsinks. So this wire will be connected to this collector, which is represented by a red wire here, and this one will be connected to this heatsink transistor collector terminal, which is again represented by the red wire here. This is the red wire. I will have to stick it to this one. Now comes this piece. So the collector terminals from these two transistors have been connected to the collector terminals of the transistor on this heatsink and the transistors on this heatsink. Now remains the emitter terminals here. These two also have to be connected. Now guys, these green wires that you see, which I had connected initially, which represented the base of the power transistors on the heat sinks, these will be connected to the emitter. Okay, this much is the size. Again, this much is the size. So done. So the green wire is done. Okay, it's time to connect the green terminals to the emitter. Okay, yeah, this seems fine. Yeah, done. Now this one. Yeah, done again. So guys, the circuit is simple enough. This is the driver circuit involving no IC but only transistors and resistors, and this is the main high current handling circuit. Okay, it is responsible for taking high current from the batteries and giving it accordingly to the input side of the transformer. So it's quite compact and robust, and we are done with the making part of it. So starting with the transformer placement, yeah, this seems fine. And about these wires, the black ones, big black wires, so to the thick black wires, these red wires will be connected, the collector wires. Okay, let's connect it like this. It's not going in. Yeah, one connected. Now comes the other black wire and the other red wire. Yeah, that also done. So the collector wires have been connected to the transformer. So with that being said, let's place a battery. So again, I'm going to use this 12 volt 7Ah battery, because what's an inverter without a battery? I could use a 12 volts power supply, but this represents an inverter better. Okay, so starting the connections. First comes the positive terminal, this one. Okay, and the batteries are really used ones, like around 6 years or 5 years old. Anyways, the positive center tap terminal of the transformer has been connected to the positive terminal of the battery. The 220 volts output terminals are here, although these two wires are going to produce much more voltage, around 400 volts. But the good thing is that we have tappings here to control the voltage according to our requirements, and this being the negative terminal. So starting with the multimeter first, okay, pointing it towards 750 volts AC. Well, I've connected only one wire, and I'm not going to connect the blue one, okay, because I'm going to check it tapping wise, like the voltage is here and then here, then here and then here. This way you can see all the better. So connecting the wires. Okay, yeah, inverter has started, I can hear the sound. So here you can see that it is producing around 68 volts AC, 130 volts AC, here around 180 volts AC, close to 220 volts. So this point should work the best. Okay, and this one is too high, 500 volts AC. That is why I said I'm not going to use this blue wire, because the voltage is too high. Okay, so you have seen the voltage. I will show you one more thing, what happens if I short the two terminals, or the spark level, whatever you may call it. You see, very high, very heavy spark. The voltage is very high, it is going to destroy our appliances. So not useful at all, at least for an inverter project. We need a max of 200 to 300 volts, not more than that. So guys, starting with this 5 watts LED bulb, Bajaj LED bulb. And guys, I forgot, if you want to watch the making part of this circuit, you can watch it from the link provided in the description. It is really important for the making part of this inverter. Okay, one wire, the white wire has been connected. The blue is empty, as I said, not needed. And let's start it and see how the bulb glows. I will have to touch it to this terminal, this one, because it produces 180 volts AC. Okay, you see, no flickering at all, glowing perfectly. But yeah, what's so great about it, because it's just a 5 watts bulb. A small inverter can also do that. So let's go a little higher. Well, how about this 18 watts LED bulb? That is pretty big. Let's try that. Okay, again to this terminal, not this one, because this is going to burn our circuit. Okay, great, perfect, good light. Let's turn off the lights and then try. Wow, pretty good. But then again, let's go a little higher. So guys, how about these? The celebration lights. Connecting one wire over here. And like turning on the inverter. Well, this might just shock me because the insulation is not thick enough. Let's use this. Okay, this should do. Pretty good, right? I would really like to see, if I touch this terminal to this one, how bright it will glow. And this has no circuit at all. It is just, these are just incandescent bulbs. So let's try and touch it to this one, the 500 volts one. Whoa, once again. Oh, pretty bright. Nice. Our inverter is working really nice, guys. So this was quite heavy load. Now again to an even bigger load. Well, let's try this bulb. Okay. Yeah. Going to hold it like this. And see, glowing pretty good. Let's touch this one also to this terminal. It's going to produce higher voltage. Let's see if it glows brighter. Whoa, pretty good. Very bright. Well, now guys, let's go to the final piece of bulbs. 100 watts bulb, Philips. Okay, and yeah, I have a holder for this one. Okay, keep watching the screen, guys. It's very light, a little brighter. Little bright. More. Haha, full brightness. Pretty good, right? You see? Cool. Well guys, it was very bright, so I have turned off the lights to see how it works when there is no light in my lab. Okay, so trying that the final time. Now you can see that it is very bright. You see, it's a fully working, very powerful inverter, easily handling 100 watts load with a very old battery. The inverter is working really nice, guys. And there's one thing that I'm thinking about is why I've connected this blue wire. I'm going to remove this blue wire and connect it to this tapping point, because this one is this is the one that I need the most. It is producing 180 volts. Yeah, this one connected to this tapping point. Let's check it if the connections are working perfect. Yeah, perfect. Now guys, many of you might have already seen this one. It's a universal motor from a drill machine, 350 watts. So you might have watched many videos about inverter making, but this inverter is really special. It has no IC or microcontroller, but still the output is almost sine wave, because of which it can also run motors. You see? Well guys, you might have seen many videos about inverter. They like place a lot of transistors or MOSFETs or even ICs, integrated circuits, and then simply run a 60 watts or a 40 watts incandescent bulb and claim that it's a 1000 watts inverter or a 5000 watts inverter. But if an inverter can actually run an inductive load, a motor, then it's a good inverter, okay, as this one. So yeah, as you can see that it is working really nice.
Next level.